have defined what are streamlines, what are path lines, what are streak lines, and then we also seen physically what do they mean, represent terms of figures, had some animation and simulations. We also saw the mathematical expressions for them. What we will do now is take two examples and illustrate how do you really calculate them. First example is a steady state velocity field, second is a unsteady state velocity field. This example is from Fox and McDonald. What you have here is a flow in a corner. This is a corner and then you have a flow in a corner. So, some flow happens like this and that is a velocity field. So, velocity field for flow in a corner is given by this equation. So, velocity is a vector here. The first time we are coming across a velocity field where both the x component and the y component are present. In the earlier examples we had just only one component. The x component is a function of x only, the y component is a function of y only. How do you visualize this? This x velocity increases with x. So, if you move along this direction, you are moving, the velocity keeps increasing. Now, what about this y component? This y component in terms of first of all it is in the negative y direction, it is minus a y, and its magnitude increases if you go further with increase with y. Though the magnitude of this component increases as y increases. So, the x component is directed in this direction, the y component is directed in this direction. That also can be easily visualized because we have a flow in this way. Okay. Now, the units of velocity are meters per second, x y in meters, and a, the constant, is given as 0.3 second inverse. What are we asked to do? Obtain an equation for the streamline passing through the point x naught y naught 2, 8, and that point is shown here. That point is shown here. We are asked to get an equation for a streamline passing through the point 2, 8. Then, because it is a steady state velocity field, we are asked to show that equation of the path line for a particle, as we have discussed, not any streamline coincides with any path line. Path line for a particle at this location at time t equal to 0 will coincide with the streamline passing through 2, 8. So, we are asked to show that equation of the path line for a particle at x naught y naught 2, 8 at t equal to 0 is the same as the equation of the streamline. Now, we are also asked to find out what is the velocity of the particle. It is starting at this location, it has some velocity, it travels along the path line, okay, and after some t equal to 6 seconds it has a velocity. We are asked to find out what is its velocity. Okay. So, let us go ahead. Let us first see how to calculate the streamlines. Okay. What is given to us is the velocity field. I have written the components here. Earlier we had in the as a vector. So, the x component is a x, the y component is minus a y. Now, we have seen the equation for streamline is that dy by dx is equal to vy by vx. This is the slope of the streamline, this is the tangent of the angle made by the velocity vector with the x axis. This condition came up because streamline is a line for which if you draw a tangent that represents the velocity. Now, just do a simple rearrangement so that you can integrate. So, write this as dy by vy is equal to dx by vx. The reason for writing this is If you substitute for V y Vx, you can integrate. Now, I substitute for Vy as minus Ay and substitute for Vx as Ax. Okay. Now, we integrate. If you integrate the left hand side, you have ln y. I have taken the negative sign to the right side. So, I get minus ln x. Integration left hand side gives ln y, minus to the right hand side. So, minus ln x, and we take the constant as ln c for convenience. So, that this equation can be represented as x y equal to c. Now, x y equal to c of in this particular case represents a hyperbolic equation x y, and that is what we are represented as streamlines here. Now, this c differs from one streamline to the other streamline. How does it get determined? It gets determined based on the point through which the streamline passes. That is why we were given find the equation of a streamline passing through a point 2, 8. Now, so plot a family of streamlines. Remember, when you draw several streamlines, you can draw tangents to all the streamlines at different locations, get the velocity field in the entire region, velocity vectors in the entire region. So, plot a family of streamlines by varying parameter c. So, for one streamline you have one value of c. Now, c depends on the point through which the streamline passes, in this particular case 2, 8. So, for streamline passing through 2, 8, what do we have? We substitute naught y naught, 2 into 8 gives you 16. So, the equation of streamline passing through 2, 8 is x y equal to 16. This is the general expression for set of streamlines. Okay. All the streamlines for this flow field are represented by this general equation x y equal to c. Based on the point you specify, or based on which streamline you want, how do you specify? You specify a point on the streamline, then this constant keeps changing. Okay. And this center one is the streamline x y equal to 16. Now, how do we calculate a path line? Now, whatever integration we have seen earlier will become clear now. Okay. We start with the velocity field. Given velocity field Vx equal to Ax, Vy equal to minus Ay. Okay. Now, path lines are the path followed by fluid particles, and from a time t equal to 0 to t equal to given time, let us say 0 to 2 seconds, 0 to 5 seconds, etc. Okay. Now, how do we start? The velocity of the particle in the x direction is given by the rate of change of its x coordinate. Okay. Now, remember we have used this principle that at a particular point at an instant, the velocity of the fluid particle is same as that of the local velocity given by the velocity field relating the Lagrangian viewpoint to the Eulerian viewpoint. That is why I equate this to Vx. When I say this, it is velocity of the particle in the x direction is equal to the velocity of the flow field in the x direction, which is equal to Ax. So, dx by dt, this is equal to dx by dt because it is Lagrangian viewpoint, gives the rate of change of position of the particle along the x direction. Similarly, for the y direction, velocity of the particle in the y direction is dy by dt, where y represents the position of the particle, that we equate to the velocity given by the velocity field in the y direction, which is minus Ay. So, by equating this, we use our principle which I have used several times, equating velocity particle to the velocity field at that location at that instant. Okay. Now, we have got two ordinary differential equations, dx by dt is equal to Ax. Okay, another differential equation dy by dt is equal to minus Ay, two equations. Now, to solve them we need initial conditions. At time t equal to 0, the particle is at x naught and y naught. To solve the differential equations, first order differential equation, we need one initial condition for this and one initial condition for this equation. That is what we are given in terms of the initial position of the particle. Now, we will integrate this equation, do a variable rearrangement, bring left hand side dx by x, right hand side a dt, integrate, you get ln x left hand side, right hand side at, take the constant as ln c1, and if you take this as ln e power at, the equation for the position of particle along the x direction is given by c1 e power at. So, x gives the, what does x represent? X coordinate of the particle as a function of time, c1 is a constant yet to be determined. Now, we will use the initial condition at time t equal to 0, we have x equal to x naught. So, substitute t equal to 0 here, x equal to x naught here. So, c1 becomes x naught. So, this is the equation with c1 evaluated now as x naught. So, when t equal to 0, you get the initial x coordinate. So, this gives you as a function of time what is the x coordinate of the particle. Now, let us do this for y direction also. So, I take this differential equation, dy by minus Ay equal to dt, integrate the left hand side, I get ln y, minus taken to the right hand side, I get minus at for the right hand side, and then the constant is taken as ln c2. Once again, this can be expressed as y is equal to c2 e power minus at. We will have to evaluate the constant c2. Once again, use the initial condition at t equal to 0, the y coordinate of the particle is y naught. So, substitute here t equal to 0 and y is y naught. So, c2 becomes y naught, and this is the equation which gives you the y coordinate of the particle as a function of time. Okay. These two put together constitute the path line for the particle. Okay. So, at an instant t, find x and y, the position of the particle. So, if you give time, I can find out x and find out what is y. Okay. And for a range of time to the given time, you can find out all the x and y coordinates and then plot the path line. Okay. The time t varies along the path line. So, and so we can eliminate the time t to plot y versus x. Okay. So, how do you do that? We have got the equation for x, we got the equation for y, and eliminating t means that let us say express t in terms of x and substitute here, or can be done as shown here, e power at from this equation is x by x naught, e power at from this equation is y naught by y because it is e power minus at. So, from this equation you can write x y equal to x naught y naught is equal to a constant. So, what is the use of this equation? If you give me time, I can find out what is the x coordinate of the particle, I can find out what is the y coordinate of the particle. What is the use of this equation? If you give me the x axis and y axis, I will straight away plot the path line. At every time I find out what is x, what is y, what is x, what is y, that is the utility of these two expressions. This straight away gives me what is the equation of the path line in x y coordinate. what they are asked is the equation of path line passing through 2, 8. The question was prove that the equation of path line for a particle which starts at 2, 8 at t equal to 0 is same as that of the streamline. So, equation of path line passing through 2, 8, which means that the particle is at 2, 8 at t equal to 0. So, x naught is 2, y naught is 8. So, x y equal to 16 is the equation of the path line, which was also the same as the equation of the streamline, okay, same as equation of streamline. Okay. We have seen that for steady flow we also have demonstration through flow between parallel plates that path lines and streamlines coincide for steady flow. We have seen another example now where path line coincides with streamline in terms of equation as well. Okay. So, let us have a demonstration here. What is shown here are different fluid particles, and then we are going to see the path line followed by each of this fluid particle. Remember we said path line is for a particular fluid particle. So, if you track this you will get one path line, if you track this you will get the second path line, etc. Okay. And now let us run this. So, these are the path lines followed by different fluid particles. This represents their position at time t equal to 0, and then these are the x y coordinates at different times. Remember along a path line time varies, t equal to 0 here and t increases along the path line here. Okay. Now, we have seen that of course the same equation as that of a streamline. Okay. Okay. The third part of the question was to find out the velocity of the fluid particle at some time instant along its path line. Okay. Let us see how do we do that. Velocity of particle at a point x comma y is equal to velocity of fluid at x comma y given by velocity field. This we have seen several times relating a Lagrangian viewpoint to the Eulerian viewpoint. So, the velocity of the particle is equal to the velocity of the fluid. Okay. Now, from the path line equations for the individual coordinates, we know what is the position of the particle as a function of time, both the x coordinate and the y coordinate. Okay. Now, we know of course the x component of the velocity field and y component of the velocity field. A is also given to us. At t equal to 0, of course we know the position of the particle is x naught y naught and then which is 2 and 8. So, if you substitute the x value here, you will get the velocity in the x direction and velocity in the y direction. When I say velocity, two ways of interpreting this: velocity of the particle in the x direction, velocity of the particle in the y direction, which also is the same as velocity of the flow field in the x direction, velocity of the flow field in the y direction. Okay. Now, as we have seen to begin with, the x velocity is a smaller value in terms of magnitude 0.6 and the y velocity is a larger value of minus 2.4 meter per second in terms of magnitude. Okay. A larger y component and a smaller x component. So, particle here will have these values 0.6 in the x direction and 2.4 in the y direction, negative y direction. What is it we are asked to find out? Let us say the particle travels over 6 seconds, what is its velocity? Now, as I told you, this set of equations gives you the x coordinate and y coordinate particle as a function of time. So, let us substitute this equation t equal to 6. So, this will be the position of particle 12.1 and the y coordinate of the particle will be 1.32. So, we are somewhere here, we are in this streamline. So, we are somewhere here, somewhere roughly here. Okay. at t equal to 0 the particle was here, at t equal to 6 seconds the particle is somewhere here. Now we know the position, and as usual as we have done earlier we can find out what is the x component of velocity and the y component of velocity. Once again represents the velocity of the fluid particle and the field as well, velocity field as well. Now if you see these values, the x component is a large value 3.63 meters per second, and y is a small negative value relatively, just minus 0.4 meter per second. Okay. That is why the in terms of angle, this the velocity vector here would make, for example in this particular case the velocity vector would make I think roughly about 70 degrees with the or 75 degrees with the x axis, but this velocity vector would make just make roughly about 6 degrees. Okay. And that is why the particle moves in this direction here along this direction, and here it is moving along this direction. So what we have done is to summarize this particular slide is we know the equation y x and y coordinate of the particle at different time instants. So if you know the time, you can find out their x and y coordinates, use the velocity field and use this physical concept of Lagrangian Eulerian equality and find out the velocity of the particle.